Right now, the nearest star to our Sun is sitting 4.24 light-years away. That sounds close. It is not. Between here and there lies a region so empty that if you scooped up a cubic centimetre of it, you would find roughly one single atom floating in that space. One atom. The air you are breathing right now contains over 20 billion molecules in that same volume. The space between stars is not simply nothing. It is a near-perfect vacuum, flooded with cosmic radiation, threaded with invisible magnetic fields, and stretched across distances so vast that our fastest spacecraft would need over 70,000 years to cross just the gap to the nearest neighbouring star. What fills that emptiness is far more terrifying than the emptiness itself. If you enjoy deep dives that change the way you see the universe, take a moment to hit that like button and subscribe. It genuinely helps more than you might think, and it keeps these stories coming. Now, settle in and get yourself comfortable. Let's begin. Look up at the night sky on a clear evening, far from the glow of city lights, and you will see something breathtaking. Thousands of stars scattered across the darkness. A dense, glowing band of light cutting across the sky from horizon to horizon. Clusters and smudges of brightness are packed so tightly together that they seem to blur into one another. The sky looks full. It looks crowded. It looks like the universe is bursting with matter, light, and energy crammed into every available corner of the cosmos. This impression is one of the greatest optical illusions in nature. Those stars that appear to sit side by side in the sky are not neighbours. They are separated by distances so extreme that light itself, the fastest thing in the universe, needs years to travel between them. The two stars that form a close visual pair in your favourite constellation might actually be hundreds of light-years apart in three-dimensional space, one vastly closer to you and the other unimaginably farther away, with no physical connection between them whatsoever. The night sky flattens the universe into a dome. It compresses trillions of miles of depth into what looks like a painted ceiling. And because of that compression, we walk through our lives believing that space is a place filled with stars. It is not. Space is a place filled with space. The overwhelming majority of the volume of our galaxy contains no stars, no planets, no moons, no asteroids, no comets. Between one star and the next lies a region so devoid of anything recognizable that it challenges the human brain to even imagine it. If you could somehow stand in the middle of the gap between our Sun and its nearest stellar neighbour, Proxima Centauri, and look around in every direction, you would see nothing. Not darkness, the way you experience it in a room with the lights off. Darkness on a scale that has no edges, no walls, no floor. A blackness so complete and so vast that it extends for trillions of miles in every direction before the next point of light appears. There is no sound. There is no wind. There is no warmth. And there is almost no matter. Almost. This is where most people stop thinking about it. They file interstellar space under the category of nothing and move on. And this is exactly where the real story begins. Because the space between stars is not nothing. It is something. It has structure. It has composition. It has behaviour. And understanding what it actually is, what fills those incomprehensible gaps between the stars, reveals a truth about the galaxy that most people never encounter. Scientists call it the interstellar medium. The name sounds clinical, almost boring, like a technical footnote buried in an astrophysics paper. But the interstellar medium is one of the most important environments in the entire Milky Way. It is the material that fills the space between the stars, and it is not empty vacuum. It is an incredibly thin, incredibly vast sea of gas, dust, charged particles, magnetic fields, and high-energy radiation that stretches across the full width of the galaxy. Every cubic centimetre of the space between stars contains some trace of this material. It is everywhere. It is always there. and it plays a role in nearly every major process the galaxy performs, from the birth of new stars to the death of old ones. Here is what the interstellar medium is made of. By mass, approximately 99% of it is gas. The remaining 1% is dust. That ratio alone tells you something important. When scientists talk about what exists between the stars, they are overwhelmingly talking about gas, not thick, breathable gas like the atmosphere you are sitting in right now. Gas so thin, so diffuse, so spread out across such enormous volumes that it makes the best laboratory vacuum on Earth look like a thick soup by comparison. But it is gas nonetheless, and it has a composition that traces directly back to the earliest moments of the universe. Roughly 70% of the interstellar gas by mass is hydrogen. This is the simplest element in existence: one proton, one electron. It is also the most abundant element in the universe, a direct product of the Big Bang itself. Nearly all the hydrogen that exists between the stars today was created in the first few minutes after the universe began, when temperatures were high enough for protons to form, but the universe was expanding too quickly for most of them to fuse into heavier elements. That primordial hydrogen has been drifting through galaxies ever since, collecting in some regions, dispersing in others, occasionally collapsing under gravity to form new stars, and then being recycled back into interstellar space when those stars die. The next most abundant component is helium, making up roughly 28% of the interstellar gas by mass. Helium was also produced during Big Bang nucleosynthesis, in the first minutes of cosmic time. Together, hydrogen and helium account for nearly all the gas in the interstellar medium. Everything else, carbon, oxygen, nitrogen, iron, silicon, every element heavier than helium that exists between the stars adds up to less than 2% of the total mass. Astronomers sometimes refer to all these heavier elements collectively as metals, which is a source of endless confusion for anyone who studied chemistry, because in this context, oxygen counts as a metal, and so does carbon. The convention is a quirk of astronomical history, but the point it conveys is accurate. The space between stars is dominated almost entirely by the two lightest elements in the periodic table. Everything else is a trace. That remaining 1% of the interstellar medium, the dust, is something entirely different. Interstellar dust is not like the dust that accumulates on your bookshelves. It is composed of tiny solid particles, typically less than a micrometer across, made of silicates, carbon compounds, and in some cases, coatings of ice-water ice, carbon monoxide ice, ammonia ice. These grains are incredibly small, roughly comparable to the wavelength of visible light, which is precisely why they are so effective at blocking and scattering starlight. When you see a dark lane running through a photograph of the Milky Way, you are looking at interstellar dust clouds so thick that they absorb the light from billions of stars behind them. The dust does not just passively sit there, it absorbs light at shorter wavelengths, particularly blue light, and re-emits that energy as infrared radiation. This process, called interstellar reddening, makes distant stars appear redder and dimmer than they truly are. For centuries, it fooled astronomers into underestimating the size of the galaxy and the distances to faraway objects, but describing the interstellar medium as simply gas and dust gives a misleading impression of uniformity. The interstellar medium is not a smooth, evenly distributed fog. It is one of the most wildly variable environments in the galaxy. Different regions of the space between stars exist in dramatically different physical states, and scientists have identified several distinct phases that coexist and interact across the galaxy. The first is the cold neutral medium. This is gas that has cooled to temperatures around 50 to 100 Kelvin, which is roughly negative 200 degrees Celsius. At these temperatures, hydrogen exists primarily in its neutral atomic form, meaning the electrons are bound to the protons and the gas carries no net electrical charge. The cold neutral medium tends to concentrate in relatively dense clumps and clouds, and it makes up a significant fraction of the total mass of the interstellar medium, despite occupying only a small fraction of the total volume. These clouds of cold neutral hydrogen are the raw material from which molecular clouds can form, and molecular clouds are the places where new stars are born. Then there is the warm neutral medium. This is hydrogen gas at temperatures around 6,000 to 10,000 Kelvin. It is still electrically neutral, atoms with their electrons intact, but it is far warmer and far more diffuse than the cold phase. The warm neutral medium fills a much larger fraction of the galaxy's volume, spreading out between the denser cold clouds like an ocean between islands. It represents one of the most common states of interstellar gas by volume. Next comes the warm ionized medium. At similar temperatures to the warm neutral medium, around 8,000 Kelvin, this phase differs in one critical respect. The hydrogen is ionized. The electrons have been stripped from the atoms, primarily by ultraviolet radiation from hot, massive stars. The warm ionized medium fills an enormous volume of the galaxy, particularly in regions near stellar nurseries and in the galactic halo above and below the plane of the disk. It was largely invisible to early astronomers because ionized hydrogen at these temperatures does not produce the same strong radio signatures as neutral hydrogen. Its detection required specialized observations of faint emission lines, particularly a spectral line called hydrogen alpha. The warm ionized medium was a relatively late addition to our understanding of interstellar structure, and its full extent is still being mapped. Finally, there is the hot ionized medium. This is the most extreme phase of the interstellar gas. Heated to temperatures exceeding 1 million Kelvin by the shock waves from supernova explosions, this phase consists of extremely diffuse, fully ionized plasma. The density is astonishingly low, as little as 1/10,000th of an atom per cubic centimeter, but its temperatures are extraordinary. Supernovae are the primary engines that create this phase. When a massive star reaches the end of its life and detonates, the blast wave expands outward at thousands of kilometers per second, sweeping up, heating, and ionizing the surrounding interstellar gas. These expanding bubbles of superheated plasma can persist for millions of years and can grow to hundreds of light years in diameter. The hot ionized medium is thought to fill a large fraction of the galactic volume, perhaps as much as 50% in some models, creating a pervasive network of overlapping bubbles and tunnels of million-degree gas threading through the cooler phases. These four phases do not exist in isolation. They are in constant interaction. Cold clouds are embedded within warmer gas. Supernova shock waves crash into dense molecular regions, sometimes compressing them enough to trigger gravitational collapse and new star formation, and sometimes blasting them apart and dispersing their material into the surrounding volume. The interstellar medium is a dynamic, turbulent, constantly churning system. Material cycles between phases over millions of years. Gas cools, condenses, forms stars, gets heated and dispersed by those stars, cools again, and the cycle continues. The galaxy is not a static painting. It is a living system, and the interstellar medium is the circulatory system that drives it. Our own solar system sits inside one of these dynamic features. It is called the local bubble, and it is a region of the hot, ionized medium that extends roughly 1,000 light-years across. The local bubble was likely carved out by a series of supernova explosions that occurred between 10 and 20 million years ago. Those explosions swept away the denser interstellar gas that had previously occupied this region, leaving behind a cavity of extremely low density, high temperature plasma. We live inside this cavity. When you look at the night sky, you are peering out through the walls of a bubble blown by dead stars. Immediately surrounding the solar system within this larger bubble is a smaller structure called the local interstellar cloud, sometimes referred to as the local fluff. This is a relatively warm, partially ionized cloud of gas with a density of roughly 0.3 atoms per cubic centimeter, slightly denser than the surrounding bubble but still extraordinarily rarefied by any terrestrial standard. The Sun is currently passing through this cloud, and it is the interstellar material that Voyager 1 and Voyager 2 first encountered when they crossed beyond the heliosphere, the bubble of solar wind that surrounds our solar system. The local interstellar cloud has a temperature of approximately 6,000 to 7,000 Kelvin and is flowing through our neighborhood of the galaxy at roughly 26 kilometers per second. In a few thousand years, the solar system will leave this cloud and enter a different region of interstellar space, possibly one that is denser or more tenuous. The environment between the stars is not static, even in our own tiny corner of the galaxy. There is one more component of the interstellar medium that most people never hear about, but that pervades the entire space between stars: magnetic fields. The galaxy is threaded with magnetic fields that extend across thousands of light years, typically measuring a few microgauss in strength. A microgauss is an almost inconceivably weak unit of magnetic force. The refrigerator magnet on your kitchen door is roughly 10 million times stronger than the interstellar magnetic field. But what the interstellar field lacks in intensity, it compensates for in scale. These magnetic fields stretch across the entire galactic disk and into the halo, influencing the motion of charged particles, shaping the structure of the interstellar gas, and playing a critical role in how cosmic rays propagate through the galaxy. Without interstellar magnetic fields, the behavior of the medium would be fundamentally different, and the galaxy would look nothing like it does today. Cosmic rays themselves are another omnipresent component of the interstellar environment. These are not rays in the traditional sense. They are particles, primarily protons but also heavier atomic nuclei, that have been accelerated to extraordinary energies by violent astrophysical events, particularly supernova remnant shockwaves. Some cosmic ray particles travel at 99.9% of the speed of light. They carry individual particle energies that can exceed anything produced by the most powerful human-built particle accelerators on Earth. These particles zip through the interstellar medium constantly, deflected and scattered by the magnetic fields, interacting with the gas and dust, and penetrating deep into any structure they encounter. They are a permanent feature of the space between stars, an invisible rain of high-energy particles that fills the galaxy from edge to edge. So let us take stock of what actually exists in the space between stars. It is not nothing. It is a sea of gas, primarily hydrogen and helium, arranged in multiple coexisting phases at vastly different temperatures and densities. It contains tiny but astrophysically important grains of dust that absorb and scatter light, reshaping what we can see. It is permeated by magnetic fields that extend across thousands of light years and influence the motion of charged particles. It is saturated with cosmic rays, high-energy particles that travel at nearly the speed of light and carry enormous individual energies. And it is dynamic, shaped by the explosions of dying stars, the radiation of living ones, and the gravitational interactions of the galaxy itself. This is the environment that lies between every star you have ever seen. Not vacuum, not void, not nothing. A structured, complex, physically real medium that scientists have spent decades studying and still do not fully understand. Every phase transition, every interaction between shockwaves and cold clouds, every magnetic field line threading through the galactic disk represents a piece of an ongoing puzzle that connects the largest scales of galactic evolution to the smallest scales of atomic and molecular physics. And here is the crucial detail that most people miss entirely. The interstellar medium is not just a backdrop, it is a participant. Without it, no new stars could form. Stars are born when regions of the interstellar medium, specifically the cold, dense molecular clouds, collapse under their own gravity. If the interstellar medium did not exist, star formation would have ended billions of years ago when the first generation of stars consumed the available material. The galaxy would be a graveyard of dead stellar remnants with no new light to replace them. Instead, the interstellar medium acts as a reservoir. Stars form from it, live their lives, and then return their material back into it through stellar winds, planetary nebulae, and supernova explosions. often enriched with heavier elements forged in their cores. The next generation of stars forms from this enriched material, incorporating those heavier elements into planets, moons, and ultimately the chemistry of life. Every atom of carbon in your body, every atom of oxygen you breathe, was manufactured inside a star, ejected into the interstellar medium, drifted through the space between stars for millions of years, and then was swept up into the collapsing cloud that formed our solar system. The interstellar medium is the bridge between stellar generations. It is the mechanism by which the galaxy renews itself. Understanding this changes everything about how we should think about the space between stars. It is not an absence, it is a presence. A thin, vast, structured, and essential presence that defines the character of the galaxy. But there is a trap in this understanding, and it is easy to fall into. Learning that the interstellar medium is not empty can create the impression that it is therefore substantial, that it is filled with useful material, that there is something out there to work with. There is not, because for all its scientific importance, for all its role in galactic evolution, the interstellar medium is staggeringly, almost incomprehensibly thin. The fact that it contains something does not mean it contains enough of anything to matter on any human scale. The gas densities we have been discussing, 1 atom per cubic centimetre in typical regions, a fraction of an atom per cubic centimetre in the hot phase, are so low that they represent conditions more extreme than any vacuum humans have ever created in a laboratory. The interstellar medium exists. It is real. It is measurable. And it is, for all practical purposes, as close to nothing as the universe can get while still technically being something. This tension between the interstellar medium being scientifically significant and practically negligible is the heart of the story. And it is a tension that only sharpens as we move deeper into the true scale of what lies between the stars. Because the emptiness of the interstellar medium is not just an abstract physical fact, it is a barrier. And the distances across which that emptiness stretches are far larger and far more terrifying than most people have ever been told. Let us begin with a single cubic centimetre. Hold your thumb and forefinger about a centimetre apart. That tiny gap, roughly the width of a pencil eraser, defines a volume of space so small you could fit hundreds of them inside a teaspoon. Now consider what that volume contains, depending on where in the universe it happens to be. At sea level on Earth, that cubic centimetre of air holds approximately 2.5 times 10 to the 19th power molecules. That is 25 quintillion. Written out, it is a 2 followed by a 5 followed by 18 zeros. Every cubic centimetre of every breath you take contains that many molecules of nitrogen, oxygen, argon, and trace gases, all bouncing off one another billions of times per second, creating the pressure and temperature you feel as the ordinary atmosphere of a pleasant afternoon. Now move that cubic centimetre into the best vacuum chamber ever built by human engineers. The most advanced ultra-high vacuum systems in research laboratories can pump a chamber down to a few thousand molecules per cubic centimetre. That is a reduction by a factor of more than 10 quadrillion compared to sea level air. At those densities, individual molecules travel for kilometres between collisions. These are the conditions required for manufacturing semiconductors, studying surface physics, and simulating aspects of the space environment for satellite testing. They represent the most extreme emptiness that human technology can reliably produce. Now move that cubic centimetre into the space between stars. In a typical region of the interstellar medium, that same cubic centimetre contains approximately 1 atom. 1. Not 100. Not 1,000. One single hydrogen atom drifting in a volume that, on Earth, would hold 25 quintillion molecules. In the hot, ionized phase of the interstellar medium, the number drops further. It can fall to 1 atom per every 10,000 cubic centimetres. Imagine a volume the size of a large moving box, the kind you would use to pack dishes when changing apartments, and place inside it a single hydrogen atom. That is the density of the hottest, most diffuse phase of the gas that fills the space between the stars. These numbers are worth pausing over because they destroy a common misconception. When people learn that interstellar space is not truly empty and that it contains gas and dust, there is a natural tendency to picture something like a very thin fog, a haze, a faint mist that you might be able to detect if you squinted hard enough. That image is wrong by a margin so vast it barely qualifies as the same category of physical experience. The interstellar medium is not a thin fog. It is a vacuum so extreme that it makes the most advanced vacuum chambers on Earth look positively dense. The fact that it contains anything at all is detectable only because the volumes involved are so enormous that even one atom per cubic centimetre, accumulated across trillions upon trillions of cubic centimetres, adds up to a measurable quantity of matter. On any human scale, on any scale that your body or your senses or your engineering could interact with, the interstellar medium is indistinguishable from perfect emptiness. Here is another way to grasp this. Take all the interstellar gas contained within 1 cubic light-year of space. A cubic light-year is an enormous volume, roughly 9.5 trillion kilometers on each side. That is a box so large that light itself would need a year to cross it. Now, take every atom of gas inside that volume and compress it down into a solid sphere at the density of water. The resulting sphere would be remarkably small. Despite starting with a volume that dwarfs the entire solar system, you would end up with a ball roughly the size of a single planet. All the matter in a cubic light-year of interstellar space, squeezed together, would fit inside something no larger than Jupiter. 1 planet's worth of material spread across a volume that light takes a year to cross. The rest of that cubic light-year, the overwhelming, crushing majority of it, is void. This is the reality that the night sky hides from you. The galaxy is not made of stars. The galaxy is made of emptiness, with stars sprinkled through it at intervals so vast that the emptiness is the dominant feature by every conceivable measure. Stars are exceptions. The interstellar void is the rule. And the void between any 2 neighbouring stars is not a small gap to be hopped across. It is an abyss. Consider the distance to the nearest star system. Proxima Centauri, the closest known star to our Sun, sits approximately 4.24 light-years away. That translates to roughly 40 trillion kilometres, 40 followed by 12 zeros. This is the shortest stellar distance in our entire neighbourhood of the galaxy, the absolute minimum gap between our Sun and any other star, and yet it is so large that human-built machines, travelling at the fastest speeds we have ever achieved, would require tens of thousands of years to cross it. To develop some intuition for what 40 trillion kilometres actually means, consider the following. The Earth orbits the Sun at a distance of about 150 million kilometres, a unit astronomers call 1 astronomical unit. Proxima Centauri is approximately 268,000 astronomical units away. If you could somehow drive a car at highway speed, roughly 100 kilometers per hour, without ever stopping for fuel or rest, you would reach the Sun in about 170 years. To reach Proxima Centauri at that same speed, you would need more than 45 million years. The dinosaurs would still be walking the Earth when you started the trip. They would have gone extinct, mammals would have risen, primates would have evolved, human civilization would have been born and possibly ended, all before you arrived. And this is the closest star. The average distance between neighbouring stars in our region of the galaxy is larger, typically around 5 light-years, but varying considerably depending on location within the galactic disk. Toward the centre of the Milky Way, stars pack more closely together, though closely still means trillions of kilometres. In the outer reaches of the galactic disk and in the halo above and below the plane, stars are spaced even farther apart. In every case, the gaps between them are filled with the same astonishingly tenuous interstellar medium we have been describing. Trillions of kilometres of near vacuum, atom by sparse atom, stretching between each island of light. This is not an academic observation. It has been directly confirmed by the only human-made objects that have ever reached interstellar space. Voyager 1, launched from Earth on September 5, 1977. Its primary mission was to study Jupiter and Saturn, which it did with spectacular success. But after those encounters, it kept going. Powered by the radioactive decay of plutonium in its 3 radioisotope thermoelectric generators, Voyager 1 continued outward from the Sun at roughly 17 kilometers per second, or about 61,000 kilometers per hour. Year after year, decade after decade, it flew. It passed the orbit of Pluto. It entered the outermost regions of the heliosphere, the bubble of charged particles and magnetic fields that the Sun inflates around itself. And on August 25, 2012, something changed. Voyager 1's instruments detected a dramatic shift in its environment. The density of charged particles around the spacecraft increased sharply. The intensity of galactic cosmic rays, high-energy particles originating from outside the solar system, jumped upward. The plasma environment transformed from one dominated by the outward-flowing solar wind to one dominated by the denser, colder plasma of the interstellar medium. After 35 years of flight and a distance of over 121 astronomical units from the Sun, Voyager 1 had crossed the heliopause, the boundary where the Sun's influence gives way to the interstellar environment, and entered the space between the stars. But this description, crossed the heliopause and entered interstellar space, makes the transition sound far cleaner than it actually was. Voyager 1 did not pass through a single doorway from the solar system into the void. It crossed a series of boundaries, each one marking a distinct physical transition, and the crossing took years, not moments. Understanding these layers matters, because they reveal just how structured the border between solar space and interstellar space truly is, and how much protection we lose when we leave. The first boundary Voyager 1 encountered was the termination shock. The Sun continuously blows a wind of charged particles outward in every direction, at speeds ranging from 400 to 800 kilometers per second. This solar wind inflates the heliosphere, pushing against the pressure of the interstellar medium, but the interstellar medium pushes back. At a certain distance from the Sun, the outward pressure of the solar wind can no longer sustain its supersonic speed against the inward pressure of the interstellar gas. The wind abruptly decelerates from supersonic to subsonic velocities, and this deceleration creates a shock wave, a standing wave in the plasma that marks the beginning of the heliosphere's outer structure. Voyager 1 crossed the termination shock in December 2004 at a distance of roughly 94 astronomical units from the Sun. Voyager 2 crossed it in August 2007 at approximately 84 astronomical units, a difference that revealed the heliosphere is not a perfect sphere, but an asymmetric structure compressed on one side by the interstellar medium's own motion relative to the Sun. Beyond the termination shock lies the heliosheath. This is a thick, turbulent region where the decelerated solar wind piles up against the surrounding interstellar medium, creating a zone of compressed, heated, chaotic plasma. The heliosheath is not calm. It is a roiling boundary layer where solar and interstellar materials interact, mix, and struggle for dominance. Magnetic fields tangle. Particle populations from both sides intermingle. Voyager 1 spent 8 years traversing the heliosheath before finally reaching the heliopause itself in 2012. 8 years of continuous travel at 17 kilometers per second, covering roughly 4 billion kilometers, just across the boundary layer between solar space and interstellar space. That single transition zone, a region most people have never heard of, is comparable to the distance from the Sun to Neptune. The heliopause is the outermost boundary, the surface where the pressure of the solar wind finally balances the pressure of the interstellar medium, and the Sun's direct influence effectively ends. This is what Voyager 1 crossed in August 2012, and Voyager 2 crossed in November 2018. Beyond it, the interstellar medium begins in earnest. But even here, the transition was not perfectly sharp. Both Voyagers detected a complex layered structure at the heliopause, with magnetic field directions shifting, particle populations fluctuating, and plasma densities changing over distances of millions of kilometers. The edge of the heliosphere is not a wall. It is a membrane, thick and textured, and crossing it is a process that unfolds over months of spacecraft travel. This layered complexity matters for a simple reason. Every layer Voyager crossed on its way out, the termination shock, the heliosheath, the heliopause, represents a component of a structure that the Sun has built around itself using nothing more than the outward pressure of its own wind. That structure took Voyager 8 years to traverse. It is not a line on a map. It is a physically thick, turbulent, multi-layered boundary between two fundamentally different environments. And once a traveller passes through all of it and emerges on the other side, there is no equivalent structure ahead for light years. The medium that awaits on the far side has been waiting for billions of years. There is one more feature of the space between the heliosphere and the nearest star that deserves attention, because it is often misunderstood as offering something it does not. The Oort cloud is a hypothesized shell of icy bodies, comets, and frozen debris left over from the formation of the solar system that is thought to extend from roughly 2,000 astronomical units out to perhaps 100,000 astronomical units from the Sun, or roughly 1.5 light years. If this shell exists as current models predict, it means the solar system's gravitational influence extends far beyond the heliosphere, reaching almost halfway to Proxima Centauri in terms of the Sun's ability to loosely hold objects in distant, fragile orbits. At first glance, this might seem encouraging. Perhaps the Oort cloud offers waypoints, resource depots, or at least landmarks along the journey to the nearest star. It does not. The Oort cloud, if it exists, is estimated to contain several Earth masses of material spread across a shell trillions of kilometers thick. The average distance between individual Oort cloud objects is estimated to be tens of millions of kilometers. You could fly through the Oort cloud for centuries and never come within visual range of a single body. The objects themselves are small, cold, and dark, frozen chunks of ice and rock drifting in orbits so distant that the Sun appears as little more than a bright star. They offer no fuel, no shelter, and no navigational utility. They are ghosts at the edge of the Sun's gravitational reach, so sparse and so scattered that they reinforce the emptiness rather than relieving it. The Oort cloud is not a resource. It is a reminder that even the solar system's most extended structure is pitifully thin compared to the gulf that separates us from the stars. Beyond the outer edge of the Oort cloud, even the Sun's tenuous gravitational claim fades. From there to the corresponding outer reaches of Proxima Centauri's own gravitational domain, there is truly nothing. No objects are in orbit around any star, no remnants of any formation process. Just the interstellar medium, atom by sparse atom, stretching across the remaining light years of the journey in perfect, featureless desolation. NASA confirmed this crossing in September 2013, based on detailed analysis of plasma oscillation data that indicated the electron density around Voyager 1 had increased by roughly a factor of 80 compared to conditions inside the heliosphere. The spacecraft had not just left the solar system's planetary region, it had left the solar system's entire protective envelope and entered a fundamentally different medium. Voyager 2 followed. Launched 16 days before its twin, but on a slower trajectory due to its detour past Uranus and Neptune, Voyager 2 crossed the heliopause on November 5, 2018. At a distance of approximately 119 astronomical units from the Sun, its crossing confirmed and expanded on Voyager 1's findings. Voyager 2 carried a working plasma science instrument that Voyager 1's had lost decades earlier, allowing it to make direct measurements of the interstellar plasma that its twin could not. The data showed that the interstellar plasma was colder and significantly denser than the plasma inside the heliosphere, exactly as models had predicted. Both spacecraft observed that the interstellar magnetic field was oriented in a direction parallel to the heliosphere boundary, a finding that surprised many scientists who had expected a sharper directional change. Since those crossings, the Voyagers have continued to send back data from interstellar space, and the findings have been consistently fascinating. In 2020, Voyager 1's magnetometer registered an abrupt increase in the intensity of the local interstellar magnetic field, accompanied by a rise in plasma density. Scientists initially interpreted these as pressure waves generated when bursts of solar activity slammed into the heliopause and sent reverberations rippling outward into the interstellar medium. But the anomaly did not fade. It persisted, leading some researchers to speculate that Voyager 1 might have entered a distinct region of interstellar space, perhaps a localized cloud of ancient plasma or a pressure structure not previously predicted by models. The investigation was interrupted in November 2023 when a hardware failure in Voyager 1's flight data subsystem caused the spacecraft to stop transmitting usable data. After months of painstaking remote troubleshooting across a signal delay of more than 22 hours each way, engineers traced the problem to a corrupted memory chip, likely damaged by a cosmic ray strike. By mid-2024, science data from multiple instruments had been restored, and the investigation of the interstellar anomaly resumed. These are extraordinary achievements of engineering and perseverance, and they reveal something profoundly humbling. As of early 2025, Voyager 1 is approximately 165 astronomical units from the Sun. That is roughly 24.7 billion kilometers. It is the most distant human-made object in existence, and it has been traveling for nearly 48 years. At its current velocity of 17 kilometers per second, it covers roughly 535 million kilometers per year. That sounds fast. It is fast by any standard of human experience. You could circle the Earth more than 13,000 times in a year at that speed, but Proxima Centauri is 4.24 light-years away. That is approximately 40 trillion kilometers. Voyager 1, after nearly half a century of continuous flight, has travelled less than 0.1% of that distance. If Voyager 1 were aimed directly at Proxima Centauri, which it is not, it would need over 70,000 years to arrive. 70,000 years. That is roughly 10 times longer than all of recorded human civilization. When Voyager 1 hypothetically arrived, the species that launched it might no longer exist. Voyager 2, slightly slower and slightly closer to the Sun, tells the same story. Both spacecraft are moving through interstellar space at speeds that dwarf anything humans experience in daily life, and both are barely crawling relative to the distances they would need to cover to reach even the nearest neighbouring star. The interstellar medium they are now sampling, the thin plasma and the elevated cosmic ray flux, and the faint magnetic field, extends ahead of them for light years in every direction. They will spend thousands of centuries drifting through this medium before they come anywhere close to another stellar system. This is the first visceral lesson about the space between stars. It is not just empty, it is vast on a scale that makes human technology irrelevant. Our fastest machines, products of decades of engineering and billions of dollars of investment, enter interstellar space and are immediately rendered negligible by the sheer distance to the next destination. The interstellar medium does not need to block you or destroy you or push you back. It simply needs to exist at the scale it exists at. The emptiness itself is the obstacle. The distance itself is the wall. And the distance to Proxima Centauri is, cosmically speaking, trivially small. It represents the very shortest interstellar gap in our region of the galaxy. Most stars in the Milky Way are separated by far greater distances. Travel to a star 10 light-years away and you have multiplied the problem by more than 2. Travel to a star 100 light-years away, still a negligible distance within a galaxy that spans 100,000 light-years, and you have multiplied it by more than 20. The interstellar medium stretches across all of it, the same sparse atoms, the same near vacuum, the same cosmic silence. There is nothing between here and there that changes the equation. Just the medium, thin and featureless and unyielding, for trillions upon trillions of kilometers. Let us put the Voyager distance into one more frame to make the point inescapable. Imagine shrinking the solar system so that the Sun is the size of a grain of sand, roughly 1 millimeter across. At this scale, the Earth would be a speck of dust orbiting about 10 centimeters away, roughly the width of your hand. Jupiter would be another tiny grain about half a meter out. Neptune, the outermost major planet, would sit about 3 meters from the Sun's grain. The entire solar system, from the Sun to Neptune, would fit comfortably inside a small room. At this same scale, Proxima Centauri would be another grain of sand sitting approximately 29 kilometers away. Nearly 30 kilometers of empty space between 2 grains of sand in a small room. Walk out of the room, through the hallway, out of the building, through the city, past the suburbs, and into the countryside for almost 30 kilometers before you reach the next grain. That is the distance between stars, scaled down to something you can hold in your hand, and everything between those 2 grains, every millimeter of those 29 kilometers, is the interstellar medium. Nearly empty, nearly featureless, just space stretching on and on and on. There is a reason this scale breaks human intuition. Our brains evolved to process distances measured in meters and kilometers. We developed spatial reasoning to navigate forests, track animals across savannas, and find our way back to shelter. Our cognitive architecture was built for a world where the farthest relevant distance was the horizon, maybe a few tens of kilometers on a clear day. Interstellar distances exceed our innate processing capacity by factors of trillions. We can write the numbers, we can perform the calculations, but we cannot feel them. The emotional reality of 40 trillion kilometers does not register in the same way that the emotional reality of a long walk home does. And so, we default to abstractions. We say 4 light years as though it were a comprehensible distance, when in truth it is a number so large it might as well be a magic spell. The words carry no experiential weight. This gap between what we can calculate and what we can feel is one of the reasons the space between stars is so routinely underestimated. Science fiction has trained us to imagine interstellar travel as a matter of better engines, faster ships, and more advanced technology. The stars are out there, and all we need is the right vehicle to reach them. What this framing ignores is the physical reality of what out there actually means. It means years of travel at the speed of light itself. It means tens of thousands of years at the fastest speeds any human technology has ever achieved. It means crossing a medium that contains, for all practical purposes, nothing useful, no fuel, no resources, no shelter, no landmarks. It means committing to a journey through a void so absolute that even the concept of progress becomes difficult to define. When the scenery does not change for millennia, when the nearest star is still light years away, when your instruments show the same sparse atoms and the same faint magnetic hum they showed a century ago, what does it mean to say you are getting closer? The density of the interstellar medium also means that there is effectively no way to harvest resources during such a journey. The concept of a Bussard ramjet, a hypothetical spacecraft that scoops up interstellar hydrogen and uses it as fusion fuel, has appeared in physics discussions and science fiction for decades. But the math is punishing. At 1 atom per cubic centimetre, a scoop hundreds of kilometres wide would collect only grams of hydrogen per second, even at high velocity. The drag created by the scoop interacting with the medium would likely exceed any thrust generated by fusing the collected fuel. The interstellar medium is simply too thin to serve as a resource. It exists, but it exists at densities so far below utility that its presence is almost taunting. There is something out there, just not nearly enough of anything. The Voyager spacecraft themselves are aging testaments to the harshness of this environment. Their radioisotope thermoelectric generators, which convert heat from decaying plutonium-238 into electricity, lose approximately 4 watts of power each year as the plutonium decays. By 2025, the power situation has grown critical enough that NASA has begun shutting down science instruments one by one to keep the remaining ones operational. In February 2025, Voyager 1's cosmic ray subsystem was powered off. In March 2025, Voyager 2's low-energy charged particle detector followed. These decisions extend the mission's life by a few years at most. Each spacecraft now operates with only 3 functioning science instruments. Engineers estimate that both Voyagers will exhaust their usable power sometime in the late 2020s or early 2030s, after which they will fall silent, drifting through interstellar space as inert artifacts, still carrying their golden records, but no longer able to tell us anything about the medium through which they travel. When the Voyagers go quiet, humanity will have no active presence in interstellar space. No instrument measuring the density of the interstellar plasma, no magnetometer tracking the faint interstellar field, no cosmic ray detector is counting the high-energy particles that saturate the medium. We will be left with the data they collected and the knowledge that, just beyond the edge of our solar bubble, a vast and almost incomprehensibly empty environment stretches outward in every direction towards stars we cannot reach. This is the scale of what lies between the stars. Not a gap, not a void to be leaped across with sufficient ambition, a medium so thin it barely registers as matter, and so vast it swallows the fastest objects humanity has ever built without the slightest notice. The interstellar medium does not care about our spacecraft. It does not resist them. It simply extends, kilometre after kilometre, light year after light year, unchanging and indifferent, while our machines crawl through it at speeds the universe considers negligible. And yet the scale is only part of the story, because for all its staggering emptiness, for all its featureless expanse, the interstellar medium is not benign. The thin gas and the sparse dust and the faint magnetic fields are not simply obstacles of distance. They carry with them something more immediate and more dangerous than mere emptiness. The space between stars is flooded with energy. High-energy particles rain through it at nearly the speed of light, every second, from every direction. Radiation permeates it at levels that would be lethal to unprotected biological tissue over any sustained exposure. The medium that seems like nothing is, in fact, actively hostile. And that hostility only grows more severe the farther you travel from the one thing that has been protecting you all along. Every second of every day, something invisible passes through your body. Not one thing, hundreds of things. Subatomic particles travelling at nearly the speed of light, remnants of catastrophic stellar explosions that occurred thousands or even millions of years ago, cross through the walls of your house, through the roof above you, through the ground beneath you, and through every cell in your body without stopping. You do not feel them, you cannot see them, they leave no trace that your senses can detect. And yet they are there, a constant rain of high-energy radiation falling from space. On the surface of the Earth, this is a minor footnote in your daily life. The planet's magnetic field deflects the majority of incoming charged particles, sweeping them into spiraling paths that funnel toward the poles rather than allowing them to strike the surface directly. The atmosphere above you, a column of gas hundreds of kilometers deep and pressing down with the weight of an ocean, absorbs most of whatever makes it past the magnetic shield. By the time cosmic radiation reaches sea level, it has been filtered, scattered, and attenuated to levels so low that the average person receives roughly 0.3 millisieverts per year from cosmic sources, a small fraction of the total background radiation exposure from all natural and medical causes combined. You live at the bottom of a double shield, magnetic and atmospheric, and that shield is so effective that most people go their entire lives without ever learning it exists. In interstellar space, both shields are gone. The heliosphere, that great bubble of solar wind plasma that the sun inflates around the entire solar system, acts as a third layer of protection that most people never think about. The solar wind, a constant outflow of charged particles streaming from the sun at 400 to 800 kilometers per second, pushes outward against the surrounding interstellar medium, creating a cavity roughly 120 astronomical units in radius. Within this cavity, the sun's magnetic field extends outward in a vast spiral, and the pressure of the solar wind keeps a portion of the incoming galactic cosmic rays at bay. The heliosphere does not block all cosmic rays. Higher energy particles punch through regardless, but it significantly reduces the total flux of galactic cosmic radiation reaching the inner solar system. Measurements from neutron monitors on Earth show that cosmic ray intensity at the surface varies with the 11-year solar activity cycle. During solar maximum, when the solar wind is strongest and the heliosphere is most inflated, cosmic ray flux drops. During solar minimum, when the wind weakens, more cosmic rays penetrate. The heliosphere is a dynamic shield, constantly breathing in and out, and everything inside it benefits from its presence. We already know what happens when you leave that shield behind. Voyager's instruments confirmed it directly. The galactic cosmic ray flux in the local interstellar medium is significantly higher than the flux inside the heliosphere. This was expected on theoretical grounds, but the Voyager crossings turned prediction into measured fact. Outside the bubble, the full intensity of galactic cosmic radiation arrives from every direction, unfiltered and undiminished. And the character of that radiation is what makes interstellar space so much more dangerous than the relatively sheltered environment we inhabit. This matters profoundly for any discussion of interstellar travel or survival beyond the heliosphere. Galactic cosmic rays are not ordinary radiation. They are not like the X-rays you receive during a dental exam or the ultraviolet light that causes sunburn. They are atomic nuclei, primarily protons, but also helium nuclei and heavier ions up to and including iron, that have been stripped of their electrons and accelerated to tremendous energies by astrophysical processes. The primary accelerators are supernova remnant shock waves. When a massive star explodes, the blast wave expands into the surrounding interstellar medium at thousands of kilometers per second. Charged particles caught in this shock wave can bounce back and forth across the shock front, gaining energy with each crossing until they reach velocities approaching the speed of light. Some galactic cosmic ray particles carry energies exceeding 10 to the 18th electron volts, and the most extreme particles ever detected reach 10 to the 20th. For a single subatomic particle, this highest energy is staggering, comparable to the kinetic energy of a fast-moving baseball concentrated into a volume smaller than an atomic nucleus. When these particles strike matter, the results are destructive at the molecular level. A single high-energy cosmic ray nucleus passing through biological tissue ionizes atoms along its track, breaking chemical bonds, damaging DNA, and creating cascades of secondary particles that spread the damage over a wider area. The heavier the nucleus, the greater the ionization damage. Iron nuclei, though they make up only a tiny fraction of the total cosmic ray flux, are particularly devastating because their high charge means they strip electrons from atoms far more aggressively than protons do. NASA classifies these heavy ions as HZE particles, standing for high atomic number and high energy, and considers them one of the most serious radiation hazards for deep space missions. The biological effects of sustained cosmic ray exposure are still not fully understood, in part because no human being has ever been exposed to the full interstellar cosmic ray environment for an extended period. Astronauts aboard the International Space Station receive elevated radiation doses compared to the surface, roughly 72 millisieverts over a 6-month mission, but they still orbit within the protective envelope of Earth's magnetic field. The station's altitude keeps it below the most intense regions of the Van Allen radiation belts, and its orbit never takes it beyond the magnetosphere. Even on a hypothetical mission to Mars, which would take astronauts outside the magnetosphere for roughly 8 to 9 months each way, the total cosmic ray dose is estimated at several hundred millisieverts, enough to meaningfully increase lifetime cancer risk, but probably survivable with careful mission planning. Interstellar space is a different category of problem entirely. Outside the heliosphere, with no magnetic field and no solar wind to attenuate the cosmic ray flux, the radiation dose rate increases substantially. Estimates based on Voyager data and cosmic ray transport models suggest that an unshielded human in interstellar space would receive a radiation dose on the order of several hundred millisieverts per year, possibly higher depending on the local cosmic ray environment. Over a journey lasting decades or centuries, the cumulative dose would be enormous, far exceeding the levels at which cancer, central nervous system damage, cardiovascular disease, and other radiation-induced pathologies become near certainties. And here is where the problem compounds in a way that defies easy engineering solutions. The instinctive response to radiation is to add shielding. Build thicker walls, surround the crew with dense material, block the particles before they reach living tissue. For ordinary radiation, this works. Lead stops gamma rays. A few centimeters of aluminum stop most solar energetic particles. But galactic cosmic rays are not ordinary radiation. The highest energy cosmic ray particles can penetrate meters of solid material. Worse, when a high-energy cosmic ray nucleus strikes a dense shield, it does not simply stop. It undergoes a nuclear reaction with the atoms in the shield material, producing a shower of secondary particles, neutrons, protons, pions, and fragments of nuclei that spray inward toward the very crew the shield was meant to protect. These secondary particles can be more biologically damaging than the original cosmic ray. Studies have shown that thin aluminum shielding, the kind used on the International Space Station, can actually increase the effective radiation dose in interplanetary space, compared to having no shielding at all, because the secondary particle production outweighs the primary particle attenuation. Thicker shielding helps, but only up to a point, and the mass required for truly effective cosmic ray shielding is enormous. Materials with low atomic numbers, such as polyethylene or water, perform better than metals because they produce fewer secondary particles, but even these materials would need to be applied in layers many tens of centimeters thick to make a meaningful difference, adding thousands of kilograms to any spacecraft design. It is worth dwelling on this secondary radiation problem because it is one of the most counterintuitive and disturbing aspects of the cosmic ray hazard, and it runs directly against every intuition we have about how shielding should work. On Earth, radiation shielding is straightforward in principle. You put a dense material between yourself and the source of radiation, and the radiation gets absorbed. Lead aprons protect dental patients from X-rays. Concrete walls surround nuclear reactors. Water pools cover spent fuel rods. In each case, the shielding material intercepts the incoming radiation and converts its energy into heat, which dissipates harmlessly. The radiation stops. The person behind the shield is safe. This principle is so reliable, so deeply embedded in our engineering practice, that it feels like a universal law. More shielding equals more protection. In interstellar space, for the highest energy galactic cosmic rays, this principle breaks down. When a galactic cosmic ray nucleus, say an iron travelling at 90% of the speed of light, strikes an aluminum hull plate, it does not gently slow down and stop the way an X-ray photon is absorbed by a lead apron. Instead, the incoming nucleus collides with an aluminum nucleus in the hull, and both nuclei shatter. The iron nucleus breaks apart into a spray of lighter fragments, protons, neutrons, helium nuclei, and pieces of heavier elements. The aluminum nucleus does the same. The collision also generates a cascade of secondary particles that did not exist before the impact. Pions, which quickly decay into muons and gamma rays, neutrons, which are electrically neutral and therefore completely unaffected by magnetic shielding, and a general shower of lower energy but still biologically damaging particles that fans out behind the impact point and penetrates deeper into the spacecraft. This is called a nuclear spallation cascade, and it transforms a single incoming high-energy particle into dozens or hundreds of secondary particles, many of which are more effective at damaging biological tissue than the original cosmic ray would have been. Neutrons are particularly insidious because they carry no electrical charge, which means they cannot be deflected by magnetic fields, and they pass easily through materials that would stop charged particles. When a neutron finally does interact with an atom in human tissue, the result is typically a heavy recoil event that deposits a large amount of energy in a very small volume, exactly the kind of interaction that causes the worst DNA damage. The net effect is paradoxical. A thin shield, say a few centimeters of aluminum, generates a significant number of secondary particles from every cosmic ray it intercepts, while failing to stop the secondaries it creates. The crew behind such a shield can receive a higher total radiation dose than they would with no shield at all, because the spallation products are more numerous and in some cases more harmful than the original cosmic ray flux. A thicker shield reduces this problem because the additional material absorbs some of the secondary particles before they reach the interior, but the improvement is slow and expensive in terms of mass. To achieve a meaningful reduction in dose from a pure aluminum shield, you would need thickness on the order of a meter or more, which translates to tens of thousands of kilograms of shielding mass for even a modest crew habitat. Lower atomic number materials, particularly hydrogen-rich compounds like polyethylene and water, perform better because lighter target nuclei produce fewer and less energetic spallation products. A proton hitting a hydrogen nucleus can only produce a recoil proton, not a shower of heavy fragments. This is why water has been proposed as a shielding material for interstellar habitats, serving the dual purpose of radiation protection and life support resource. But even water shielding needs to be applied in layers of 30 centimeters or more to make a significant difference against the full galactic cosmic ray spectrum, and the mass penalty remains severe for any vehicle that must also accelerate to interstellar velocities. The secondary radiation problem means there is no simple engineering fix for cosmic ray exposure in interstellar space. You cannot just build a thicker wall. The wall fights back. For a short duration mission to Mars, lasting perhaps 2 to 3 years round trip, the radiation problem is serious but potentially manageable through a combination of modest shielding, mission timing to coincide with solar maximum, when galactic cosmic ray flux is lower, and acceptance of some elevated long-term health risk. For an interstellar mission lasting decades, centuries, or millennia, the problem is qualitatively different. The cumulative exposure grows without limit. There is no solar maximum to time the journey around. There is no possibility of a quick return if the shielding proves insufficient. The cosmic ray environment of interstellar space is a permanent condition, and any vessel travelling through it must either carry shielding massive enough to reduce the dose to acceptable levels for the entire duration of the journey, or accept that its occupants, biological or electronic, will be steadily degraded by radiation damage the entire way. Electronics face their own version of this problem. Cosmic ray particles striking semiconductor components can cause single-event upsets, where a charged particle deposits enough energy in a transistor to flip a memory bit from one state to another. In spacecraft electronics, this manifests as corrupted data, unexpected software behavior, and in severe cases, permanent damage to circuit components. Voyager 1's 2023 communication failure, the corrupted memory chip we discussed earlier, was likely caused by exactly this kind of event. For a probe designed in the 1970s with relatively simple radiation-hardened electronics, this was a recoverable problem. For a more complex interstellar vehicle carrying sophisticated navigation, life support, and communication systems, the chronic bombardment of galactic cosmic rays would represent a continuous reliability threat that compounds over time. Every year in interstellar space is another year of radiation exposure, another year of accumulated damage to circuits, sensors, structural materials, and any biological payload. But cosmic rays are not the only hazard embedded in the interstellar medium. The dust that makes up roughly 1% of the medium by mass presents a completely different category of danger, one that scales not with time, but with velocity. Interstellar dust grains are small, typically a fraction of a micrometer across, composed of silicates, carbon compounds, and in some cases, mantles of frozen volatiles. At the densities found in the general interstellar medium, these grains are incredibly sparse. You might encounter only a few per cubic kilometer in typical conditions, and in the low-density hot phase, even fewer. At the speeds of the Voyager spacecraft, 17 kilometers per second, collisions with individual dust grains are minor events. The kinetic energy involved is tiny, and the impacts produce negligible damage. But interstellar travel proposals do not envision traveling at 17 kilometers per second. The whole point of interstellar propulsion concepts is to reach a significant fraction of the speed of light. Breakthrough Starshot, one of the most concrete interstellar proposals currently under development, aims to accelerate gram-scale probes to 20% of the speed of light using ground-based laser arrays. At that velocity, 60,000 kilometers per second, the physics of dust grain collisions changes completely. Kinetic energy scales with the square of velocity. A dust grain that barely registers at 17 kilometers per second becomes a tiny bomb at 60,000 kilometers per second. A grain of interstellar dust weighing 1/1000th of a gram, striking a spacecraft at 20% of the speed of light, releases energy equivalent to roughly the detonation of a small explosive charge. The grain does not bounce off. It vaporizes on impact, along with a portion of the surface it strikes, creating a microscopic crater and a spray of plasma and debris. Individually, these impacts might be survivable for a robust spacecraft, but accumulated over years of travel through even the sparse general interstellar medium, the total number of impacts could amount to significant surface erosion, damage to optical systems, degradation of thermal shielding, and, in worst-case scenarios, penetration of critical structural components. For crewed vessels, which would necessarily be larger and more complex than gram-scale probes, the dust problem is even more acute. Larger cross-sectional areas intercept more grains. Longer journey times mean more total impacts. And the systems at risk, windows, radiators, antenna surfaces, solar panels, are precisely the ones that are most difficult to armor without adding prohibitive mass. Some proposals have suggested forward-mounted shields or deflector systems, but these add mass, complexity, and their own failure modes. The interstellar dust hazard is not a showstopper at low velocities, but it becomes increasingly serious as the desired speed increases, which creates an uncomfortable paradox. Faster travel reduces the time spent in the hostile interstellar environment, but increases the severity of dust collisions. Slower travel reduces collision energy but extends the total exposure time to cosmic radiation and every other cumulative hazard. There is no free variable. Every parameter trades off against another. The magnetic fields of the interstellar medium add another layer of physical reality that any interstellar traveler would have to contend with. The large-scale interstellar magnetic field, measuring roughly 3 to 5 microgauss in our region of the galaxy, is extraordinarily weak by any human standard. It is roughly 100,000 times weaker than Earth's surface magnetic field and billions of times weaker than the field in a medical MRI machine. But its weakness is compensated for by its scale. The interstellar magnetic field extends coherently across parsecs, which is to say, across distances of several light years. It threads through the entire interstellar medium, influencing the motion of every charged particle within it. For a spacecraft carrying no net electrical charge, the interstellar magnetic field is essentially irrelevant as a direct force. But for any propulsion or navigation concept that involves charged particles, plasma interactions, or electromagnetic systems, the background magnetic field becomes a factor that must be accounted for. The magnetic field also governs the propagation of cosmic rays through the medium, scattering them in complex ways that make the local cosmic ray environment variable and difficult to predict in detail. Regions of enhanced magnetic field strength can funnel or focus cosmic rays, creating localized zones of higher radiation intensity. Regions of weaker or more tangled fields may allow cosmic rays to diffuse more freely. The magnetic landscape of the interstellar medium is not uniform, and a traveler moving through it would encounter varying radiation conditions along the route, some better and some worse than the average. Interstellar magnetic fields also carry energy. The magnetic pressure in the interstellar medium is comparable to the thermal pressure of the gas and the pressure exerted by cosmic rays. All three contribute roughly equally to the total pressure balance that determines the structure and dynamics of the medium. This means the magnetic field is not a passive background feature. It actively participates in shaping the interstellar environment, influencing how gas clouds compress and fragment, how shock waves propagate, and how energy is transferred across vast distances. Any model of interstellar conditions that ignores magnetic fields is fundamentally incomplete. Then there is the thermal environment, which presents its own set of challenges. The interstellar medium exists at a wide range of temperatures, from around 10 Kelvin in the coldest molecular clouds to over 1 million Kelvin in the hot ionized phase. But these temperatures are misleading in a way that many people do not immediately grasp. Temperature, in the physics of gases, describes the average kinetic energy of the particles. In the hot ionized medium, individual ions are moving at very high speeds, corresponding to temperatures of 1,000,000 degrees. But because the density is so incredibly low, the total thermal energy per unit volume is negligible. You could pass through million-degree interstellar plasma and not feel any heat at all, because there are so few particles per cubic centimetre that the total energy they could transfer to your spacecraft is vanishingly small. The real thermal problem in interstellar space is not overheating, it is heat loss. In the near vacuum of the interstellar medium, there is no convective or conductive heat transfer. The only way to shed or gain heat is through radiation, and in a region far from any star, the ambient radiation field is extremely faint. Any warm object in interstellar space, whether a spacecraft, a human body, or a piece of equipment, will slowly radiate its heat away into the surrounding emptiness. Without a star nearby to provide a continuous input of energy, maintaining thermal equilibrium requires an onboard power source. For the Voyager spacecraft, the radioisotope thermoelectric generators serve this dual purpose, generating both electricity and waste heat that keeps the spacecraft systems within operating temperature ranges. As those generators fade, the spacecraft will eventually cool to the ambient temperature of interstellar space, a few degrees above absolute zero, and all its systems will cease to function even if the electronics were otherwise intact. For a crewed interstellar vessel, thermal management would be a continuous engineering challenge for the entire duration of the journey. Reactors or other power sources would need to run without interruption to maintain habitable temperatures. Heat rejection systems, typically large radiator panels, would need to function perfectly for decades or centuries. Any failure in the thermal control system, even a partial failure, could cascade into habitability crises within hours or days, and there is no external source of warmth to fall back on, no star to orbit, no atmosphere to trap heat, just the cold, empty medium, patient and indifferent, drawing heat away from any warm body within it at the implacable rate dictated by the Stefan Boltzmann law. What makes all these hazards so insidious is that none of them, taken individually, is necessarily catastrophic over short timescales. A burst of cosmic radiation does not kill you instantly. A single dust grain impact does not destroy a spacecraft. One cold night does not freeze a habitat. The danger lies in accumulation, in the relentless compounding of small insults over enormous spans of time and distance. Interstellar space does not attack, it erodes, it degrades. It slowly, patiently wears down every system, biological and mechanical, that dares to enter it. A journey of decades through this medium means decades of continuous cosmic ray bombardment, decades of thermal management without resupply, decades of micrometeorite impacts, decades of electronic degradation, decades of radiation damage to structural materials, seals, lubricants, and polymers. Nothing in the interstellar medium is aggressive on a human timescale. Everything in it is lethal on an interstellar one. The interstellar medium is sometimes described as the vacuum of space, but this phrase understates its character. A vacuum implies absence, passivity, the mere lack of something. The interstellar medium is not passive, it is an environment. It has properties, behaviours, and effects. It pushes back, not with walls or storms, but with physics. The cosmic rays do not stop, the cold does not relent, the distance does not shrink, the dust does not clear. Every light year of interstellar medium is functionally identical to the last. presenting the same suite of low-level hazards at the same low-level intensities, and the only thing that changes is the total accumulated dose, the total accumulated damage, and the total accumulated wear. This is an environment that punishes duration, and duration is the one thing that interstellar travel demands in absolute abundance. All of this leads to an uncomfortable realization. The space between stars is not simply far, it is not simply empty. It is a physical environment that creates compounding, escalating obstacles for anything that attempts to cross it. Distance alone would be a challenge enough. But the interstellar medium adds a second layer of difficulty. It fills that distance with a thin, pervasive, inescapable medium that slowly damages everything passing through it. And there is no shortcut through it. The interstellar medium is everywhere between every star in the galaxy. It is the default condition of the Milky Way, and it is far more formidable than its near-invisible thinness would suggest. What remains to be understood is what all of this means when you pull back from the details and look at the galaxy as a whole. Because when you combine the emptiness, the distance, the radiation, and the hostility into a single picture, what emerges is not merely a list of engineering challenges. What emerges is a barrier, perhaps the most fundamental barrier in the natural universe, and one that reshapes how we must think about our place within the galaxy. Step back from the details for a moment. Forget the individual numbers. Forget the density of one atom per cubic centimetre, the cosmic ray flux measurements, and the temperature phases of the interstellar gas. Instead, try to see the galaxy the way it actually is, not as a glittering pinwheel of light, but as a physical structure defined by what lies between the light. The Milky Way contains roughly 400 billion stars. That number sounds like abundance. It sounds like a galaxy overflowing with suns, packed wall to wall with stellar furnaces and their attendant planets and moons. 400 billion is a number so large that it overwhelms intuition, and the natural conclusion is that the galaxy must be a crowded, busy place. But that conclusion is catastrophically wrong, because those 400 billion stars are scattered across a disk, roughly 100,000 light-years in diameter, and 1,000 to 2,000 light-years thick, and when you distribute even 400 billion objects across a volume that size, you get something that is overwhelmingly, crushingly empty. The galaxy is not a city of stars. It is a desert with stars in it. Consider the proportions. If you could somehow gather all 400 billion stars in the Milky Way and push them together into a single mass, that mass would occupy an almost vanishingly small fraction of the galaxy's total volume. The rest, the vast and overwhelming majority, is the interstellar medium, the thin, nearly empty, radiation-saturated, magnetically threaded void we have been describing throughout this story. Stars are bright. Stars are important. Stars are where energy is generated, where elements are forged, where planets form, and where life can emerge. But stars are not what the galaxy is made of. The galaxy is made of the space between them. By volume, the interstellar medium is the galaxy. The stars are the exceptions, tiny pockets of dense, luminous matter embedded in an ocean of near-nothingness that stretches in every direction for distances that light itself takes years to cross. This is the perspective shift that changes everything. When you look at the night sky, you see the exceptions. You see the rare concentrations of matter that manage to collapse under gravity, ignite nuclear fusion, and shine. You do not see the medium in which they float. You cannot see it. It is too thin to scatter light in any way your eyes can detect. It is too cold and too diffuse to glow visibly, except in a few specialized wavelengths that require telescopes tuned to radio or infrared frequencies. The interstellar medium is, for all practical purposes, invisible. And because it is invisible, we ignore it. We build our mental model of the galaxy around the things we can see, the stars, and we treat the space between them as though it were simply distance, a number to be overcome by better technology. But it is not simply distance, it is an environment, and that environment has properties that make crossing it one of the most difficult challenges the laws of physics permit. begin with energy. To move any object across interstellar distances within a time frame shorter than geological epochs, you need velocity. Not the kind of velocity that gets a satellite into orbit or sends a probe to Jupiter. You need a significant fraction of the speed of light. 10% of light speed, roughly 30,000 kilometers per second, is often cited as the minimum practical velocity for interstellar travel, because at that speed, a journey to the nearest star takes approximately 42 years. Slower than that, and you are looking at centuries. Faster than that, and you begin to approach timescales that a single human generation might survive, but the energy costs become staggering. The kinetic energy of a moving object scales with the square of its velocity. This means that reaching 10% of the speed of light requires not 10% of the energy needed to reach light speed, but 1%, which sounds like a discount until you calculate the actual numbers. For a spacecraft with a mass of just 1,000 kilograms, roughly the mass of a small car, accelerating to 10% of the speed of light requires approximately 4.5 times 10 to the 17th joules of energy. That is 450 quadrillion joules. For comparison, the total energy output of all the power plants on Earth in an entire year is roughly 5.8 times 10 to the 20th joules. So, accelerating a single small car-sized object to the minimum practical interstellar speed would consume roughly 1,000th of the entire planet's annual energy production. And that is just the acceleration. Slowing down at the destination requires the same amount of energy again. A round trip doubles it further. Scaling up from a 1,000 kilogram probe to a crewed vessel carrying life support, shielding, supplies, and a crew multiplies the energy requirement by factors of thousands or millions. These are not engineering problems in the conventional sense. Engineering problems have solutions that can be reached through incremental improvements in technology. The energy requirements for interstellar travel are problems of physics, dictated by the mass-energy relationship and the scale of the distances involved. No amount of clever engineering changes the kinetic energy equation. You can choose different propulsion methods: nuclear pulse, fusion, antimatter, laser sail, but every method must ultimately provide the same total energy to achieve the same velocity. The interstellar medium does not create this energy barrier directly, but it is the reason the barrier exists. If stars were separated by millions of kilometers instead of trillions, the energy requirements would be trivial. It is the sheer extent of the interstellar void, light years of almost nothing, that forces the velocity requirement so high and the energy budget so far beyond current capability. Several propulsion concepts have been proposed that attempt to address this challenge, and each one reveals how formidable the barrier truly is. Nuclear pulse propulsion, the concept explored in Project Orion during the 1950s and 60s, envisioned detonating nuclear bombs behind a spacecraft to accelerate it. Theoretical studies suggested that an Orion-type vessel could reach perhaps 3 to 5% of the speed of light using fission bombs, or up to 8 to 10% using thermonuclear devices. These are impressive figures on paper, but they require a spacecraft massing hundreds of thousands of tons, carrying thousands of nuclear weapons, and they still produce a journey time to Alpha Centauri measured in decades to centuries. The concept was never tested at scale, and the political and practical obstacles to launching a nuclear bomb-powered spacecraft from Earth are considerable. Fusion propulsion offers theoretical improvements, using the energy released by fusing hydrogen or helium isotopes to generate thrust, but sustained, controlled fusion remains one of the great unsolved engineering challenges on Earth, let alone in a spacecraft. Even optimistic projections place practical fusion rockets decades in the future, and even if they are realized, the exhaust velocities they could achieve still limit interstellar cruise speeds to a few percent of light speed without extraordinary mass ratios. Breakthrough Starshot, the laser sail initiative backed by the late physicist Stephen Hawking and investor Yuri Milner, takes a radically different approach. Instead of carrying fuel, the spacecraft is a wafer-scale chip attached to a reflective sail accelerated by a ground-based laser array to 20% of the speed of light. This concept sidesteps the fuel problem entirely by leaving the energy source on the ground. At 20% of light speed, the probe could reach Alpha Centauri in roughly 20 years. It is the most plausible near-term interstellar concept currently under serious study, and it elegantly solves the propulsion challenge for tiny, gram-scale payloads. But it solves nothing else. A gram-scale probe cannot carry meaningful shielding against cosmic rays or dust impacts at 20% of light speed. It cannot slow down at the destination. It cannot carry instruments much more sophisticated than a simple camera and a communication laser. And it does absolutely nothing for the problem of sending humans or even substantial robotic payloads across interstellar distances. Breakthrough Starshot demonstrates that it might be possible to fling a tiny chip across the interstellar medium. It does not demonstrate that the interstellar medium can be meaningfully crossed by anything resembling a mission of exploration, habitation, or survival. The most common response to the timescale problem of interstellar travel is a concept so deeply embedded in science fiction that many people treat it as an inevitability rather than a hypothesis. The generation ship. The idea is simple in principle. If no single human lifespan is long enough to complete the journey, build a vessel large enough to sustain a self-reproducing population across multiple generations. The crew that launches from the solar system is not the crew that arrives at the destination. Their great-great-great-grandchildren are. The generation ship accepts the interstellar medium's timescale and attempts to outlast it through biology rather than velocity. It is an elegant concept on a whiteboard. It is a nightmare in practice. Consider what a generation ship must actually achieve. It must sustain a human population in complete isolation for centuries, not in the sense that a submarine sustains a crew for months, with resupply missions scheduled and a return to port guaranteed. In the sense of total, irrevocable self-sufficiency, with zero external input for the entire duration of the journey. Every calorie of food must be grown on board. Every litre of water must be recycled with near-perfect efficiency. Every cubic metre of breathable atmosphere must be maintained by closed-loop life support systems that cannot fail catastrophically even once across a span of 300, 500, or 1,000 years. The ship is not a vehicle, it is a world. And it must function as a world with no margin for error over time, scales longer than any human civilization has ever remained stable. Now layer onto this the hazards of the interstellar medium. The cosmic ray flux outside the heliosphere bombards the vessel continuously for the entire journey. Over centuries, the cumulative radiation dose to the hull, the internal systems, and the population itself would be enormous. Shielding helps, but as we have discussed, shielding against galactic cosmic rays requires massive amounts of material, and every kilogram of shielding is a kilogram that must be accelerated to interstellar velocity and decelerated at the destination. A generation ship large enough to sustain a breeding population, estimates vary but typically start at several thousand people minimum to maintain genetic diversity, would need to be vastly larger and more massive than any structure humanity has ever built in space. The shielding requirements alone could dwarf the mass of the habitable volume. The structural integrity of such a vessel presents its own category of concern. Materials fatigue, seals degrade, metals suffer radiation embrittlement over decades of cosmic ray exposure, polymers break down, lubricants evaporate or decompose. Every mechanical system on board, every pump, every valve, every bearing, every seal in every airlock and pressure vessel must either last for centuries without maintenance or be replaceable using only the resources carried on board. There is no resupply. There are no spare parts from Earth. If a critical system fails in year 200 of a 500-year journey, the crew must repair it with whatever they have or die. The biological challenges are equally severe. A small, closed population living in a confined environment for centuries would face genetic bottleneck effects, inbreeding risks, and the psychological toll of multi-generational confinement. social stability over centuries is not guaranteed. Human societies on Earth, with vastly greater resources and space, routinely undergo revolutions, collapses, famines, and civil conflicts over timescales of mere decades. A generation ship would need to maintain social cohesion, institutional knowledge, technical competence, and a shared sense of purpose across dozens of generations, all while confined to a structure that, however large, would still be incomprehensibly small compared to a planetary surface. The descendants who arrive at the destination would bear no personal connection to the decision to launch. They would have been born into the journey, raised within its walls, and asked to continue a mission conceived by ancestors they never knew. Whether such a population would choose to continue, or would fracture, rebel, or simply lose the technical capacity to operate the ship, is an open and deeply troubling question. The generation ship concept does not solve the problem of the interstellar medium. It absorbs the problem and attempts to endure it through brute persistence. And every hazard the medium presents, radiation, thermal management, dust erosion, material degradation, compounds across the centuries, such a ship would spend in transit. A generation ship is not a shortcut around the barrier. It is a decision to live inside the barrier for the entire crossing, accepting every insult it delivers, for longer than most civilizations have ever lasted. There is one more dimension of the interstellar medium's barrier that we have not yet addressed, and it applies regardless of propulsion method or mission architecture. The interstellar medium is not uniform across the galaxy. Its density, temperature, radiation environment, and magnetic structure vary dramatically depending on where in the Milky Way you happen to be. And for the most part, the variations make things harder, not easier. The galaxy's spiral arms are regions of enhanced density where interstellar gas and dust concentrate, compressed by density waves propagating through the galactic disk. Within the spiral arms, molecular clouds are more common, dust extinction is higher, and the interstellar medium is generally thicker and more structured. Supernova rates are also higher in spiral arms because the denser gas fuels more vigorous star formation, which produces more massive stars that die quickly and violently. This means the cosmic ray production rate is elevated within and near the spiral arms. A vessel passing through a spiral arm region would encounter both higher gas and dust densities and a more intense radiation environment compared to the interarm regions. Between the spiral arms, conditions are somewhat more favourable. Gas densities drop, dust is sparser, and the cosmic ray flux is modestly lower. The interarm regions are the closest thing the galaxy offers to clear corridors between stars, but more favourable is a relative term. The interarm interstellar medium is still a near vacuum, flooded with cosmic radiation. It is still light years wide. It is still devoid of resources and shelter. Calling it easier to cross than a spiral arm is like saying the deep ocean is easier to swim across than a hurricane. Technically true, practically meaningless. Near the galactic center, conditions become dramatically worse. The density of stars, gas, and dust increases sharply. The radiation environment intensifies. Supermassive stellar clusters, energetic nebulae, and the supermassive black hole Sagittarius A star and its associated accretion activity create a radiation-drenched environment that is hostile at scales far exceeding the general interstellar medium. The galactic center is not a place that any known or foreseeable technology could traverse safely, even in principle. In the galactic halo, above and below the plane of the disk, the interstellar medium thins further, but the distances between stars increase enormously. Halo stars are scattered across tens of thousands of light years with vast, empty spaces between them. The medium is thinner, but the journey is longer, and the isolation is even more absolute. There is no direction you can travel in the Milky Way, where the interstellar medium becomes easy. There is no corridor, no gap, no convenient low-density tunnel connecting one star to another. The medium varies, but it never relents. Every route between any two stars in the galaxy passes through light years of structured, radiation-permeated, resource-free void. The barrier is not localized, it is galactic, it is everywhere. Every propulsion concept, no matter how advanced, runs into the same fundamental wall. The interstellar medium is too vast to cross quickly, too empty to harvest for resources along the way, and too hostile to endure for extended periods without enormous investments in shielding, power, and life support. The barrier is not any single one of these factors. The barrier is all of them, simultaneously, compounding across distances that dwarf every other scale of human experience. And there is one more element of the barrier that is easy to overlook, because it is so absolute. Between one star and the next, there is nothing to stop at. On Earth, long journeys are punctuated by waypoints. You can rest, refuel, resupply, and repair at intervals along the route. Even in the age of exploration, when European sailors crossed the Atlantic or rounded the Cape of Good Hope, they could anchor at islands, take on fresh water, patch their hulls, and continue. The ocean was vast and dangerous, but it contained stopping points. The interstellar medium contains none. Between the Sun and Proxima Centauri, there are no planets, no moons, no asteroids of any useful size, no comets, no space stations, no fuel depots, no harbours. There is nothing. Just the medium itself, thin and hostile and featureless, extending without interruption for over 4 light-years. A vessel that departs the solar system is committed. There is no turning back without expending the same energy again. There is no coasting into a convenient port. There is no rescue if something breaks. The journey is all or nothing, a crossing of a void that offers no shelter, no resources, and no second chances. This is why the concept of the heliosphere matters so deeply to the story of interstellar space. The heliosphere is not just a scientific curiosity or a boundary on a diagram. It is the last shelter. It is the final protective environment before the full severity of the interstellar medium takes hold. Inside the heliosphere, the solar wind provides a buffer against the worst of the galactic cosmic ray flux. Inside the heliosphere, the sun's magnetic field offers a measure of order and protection. Inside the heliosphere, there is a star nearby, providing energy, warmth, and a gravitational anchor that makes navigation and orbital mechanics possible. The moment you cross the heliopause, all of that ends. The cosmic ray flux jumps. The magnetic environment shifts to the interstellar field, organized on scales of light years rather than astronomical units. The nearest source of energy, the sun, begins to dwindle behind you, its light and warmth fading with the square of the distance until it is just another star in the sky, indistinguishable from the billions of others. Voyager 1 experienced this transition firsthand. Before the crossing, it existed within a bubble maintained by the sun. After the crossing, it existed in the interstellar medium, exposed to conditions that had been the default state of the galaxy for billions of years. The spacecraft did not notice, of course. It is a machine, built to endure a vacuum and radiation. But for any living thing, or any complex system dependent on long-term reliability, the transition from the heliosphere to the interstellar medium is a transition from a sheltered environment to an unsheltered one, and there is no equivalent shelter ahead. The next heliosphere, the astrosphere surrounding Proxima Centauri, does not begin until you are very close to that star, within perhaps 100 astronomical units of it. Between the edge of our heliosphere and the edge of the next, there is nothing but raw interstellar medium for the vast majority of the journey. When you hold all of this in your mind at once, the distance, the emptiness, the radiation, the dust, the cold, the absence of resources, the absence of shelter, the energy requirements, the timescales, the compounding degradation, what emerges is not a list of problems to be solved. What emerges is a picture of the galaxy itself. The Milky Way is a structure in which islands of warmth and light are separated by an ocean that is functionally uncrossable by any technology that currently exists or is likely to exist within the foreseeable future. The interstellar medium is that ocean, and it is not a passive obstacle. It is an active environment with properties specifically hostile to sustained crossing. This does not mean interstellar travel is impossible in principle. Physics does not forbid it. There is no law that prevents a sufficiently advanced civilization from building a vessel capable of enduring the interstellar medium for decades or centuries and arriving intact at another star. But the resources, the energy, the engineering tolerances, and the sheer duration required are so extreme that they place interstellar travel in a category fundamentally different from any other journey humanity has ever contemplated. Going to the moon took 3 days. Going to Mars might take 8 months. Going to the nearest star, at the fastest speeds any proposed technology can achieve, takes decades. And that is the nearest star. The overwhelming majority of the 400 billion stars in the galaxy are not 4 light years away. They are hundreds or thousands or tens of thousands of light years away, separated by proportionally vaster stretches of the same hostile medium. The galaxy is not small and is cluttered with stars. It is enormous and defined by the emptiness between them. This is why the galaxy is silent. This is why, despite hundreds of billions of stars and likely billions of planets, we detect no signals, no probes, no evidence of traffic between stellar systems. The interstellar medium is the answer. Not because other civilizations do not exist. We have no way of knowing that, but because the medium between the stars creates a barrier so formidable that crossing it may be something that very few civilizations ever achieve. And even those that do may find the cost so extreme that they do so only rarely, or on time scales so long that their efforts are invisible to us. The silence of the galaxy is not mysterious when you understand the medium. It is expected. The stars are isolated. They have always been isolated. The interstellar medium ensures it. And yet, in the midst of all this austerity, there is something else. Something that pushes back against the bleakness. Because the interstellar medium is not just a barrier, it is also a record. Every atom of gas drifting between the stars carries information about where it came from and what happened to it. The hydrogen that fills the interstellar void is primordial, forged in the first minutes after the Big Bang. The heavier elements mixed into it, the carbon, the oxygen, the iron, were synthesized inside stars that lived and died billions of years ago, their ashes scattered by supernova explosions into the medium where they now drift. The dust grains are built from those same stellar ashes, assembled atom by atom in the outflows of dying red giants and the expanding shells of supernova remnants. The cosmic rays that flood the medium are accelerated by the shock waves of those same explosions, carrying energy across the galaxy at nearly the speed of light. The interstellar medium is the galaxy's memory. It holds the chemical record of every generation of stars that has ever lived and died in the Milky Way. It contains the raw material from which the next generation of stars and planets will form. It connects the past and the future of the galaxy through a slow, continuous cycle of creation, destruction, and renewal that has been running for over 13 billion years. The same medium that isolates every star from every other star is also the medium that gave birth to all of them. Our own solar system condensed from a cloud of interstellar gas and dust, roughly 4.6 billion years ago. Every atom in the Earth, every molecule in your body, spent millions of years drifting through the interstellar medium before gravity gathered it into the collapsing cloud that became the Sun and its planets. You are made of interstellar material. The calcium in your bones was forged in a star that exploded before the Sun existed, and the atoms of that calcium drifted through the cold, thin, radiation-soaked space between the stars before finding their way into the nebula that became your world. The interstellar medium is not just the barrier that separates you from the rest of the galaxy. It is the substance from which you were made. There is a strange and disquieting beauty in this. The same environment that makes the galaxy unreachable is the environment that made you possible. The vast emptiness that isolates every star system from every other is also the vast reservoir from which every star system was born. The medium is simultaneously the galaxy's greatest obstacle and its most essential feature. Without it, there would be no barrier between the stars, but there would also be no stars to have barriers between. This is the terrifying truth about the space between stars. It is not that it is empty. Calling it empty misses the point entirely. It is that the space between stars is a physical environment, real, structured, and measurable, that creates one of the most formidable natural barriers in the known universe. The distance is the barrier. The emptiness is the barrier. The radiation is the barrier. The cold is the barrier. The absence of shelter is the barrier. The absence of resources is the barrier. Every one of these factors alone would be a serious obstacle. Together, reinforcing and compounding one another across light years of unbroken void, they form a wall that the galaxy has built around every single one of its 400 billion stars. We look up at the night sky and we see light, we see beauty, we see a possibility, and all of that is real. There are worlds out there, orbiting other suns, some of them perhaps teeming with life, perhaps home to civilizations that have looked back at our sun and wondered the same things we wonder about them. But between us and every one of those worlds lies the interstellar medium, not nothing, something vast, something hostile, something patient, and something that does not care whether we ever cross it or not. The medium will still be there in 1 billion years, thin and cold and saturated with cosmic rays, stretching between stars that have not yet been born. It is the permanent condition of the galaxy. It is the ocean we cannot sail, and perhaps that is the deepest lesson the interstellar medium has to teach us. Not that we are small, though we are, not that the universe is indifferent, though it is, but that the galaxy is structured in a way that makes isolation the default state of every star, every planet, every civilization that has ever existed or ever will. The space between stars is not a problem to be solved. It is a feature of the cosmos. It is how the galaxy is built. The stars shine in solitude, separated by light years of structured emptiness, and the emptiness is not a failure of the universe to fill itself. It is the architecture of the universe itself. We live on one small world orbiting one ordinary star, protected by a thin bubble of solar wind from the full severity of the medium that surrounds us. Beyond that bubble, in every direction, the interstellar void extends outward toward other stars we can see but cannot touch. We are not separated from the rest of the galaxy by nothing. We are separated by something, a medium so vast and so hostile that it may be the single greatest barrier nature has ever constructed. And in the face of that barrier, what we have accomplished is not insignificant. We have sent 2 small machines beyond the edge of our bubble and into the medium itself. We have measured its density, its temperature, its magnetic field, and its radiation. We have confirmed that it is real and that it is there. 2 tiny spacecraft, barely the size of a compact car, drifting at 17 kilometers per second through a void that stretches for light years in every direction, still sending data home through a signal so faint it carries less power than a refrigerator light bulb. That is what we have done so far. 2 probes in an ocean that spans 100,000 light years. It is almost nothing, and it is extraordinary.